Hopefully today goes better than this morning, which had all sorts of technical gremlins. Hopefully they're gone. Let's look at the puzzler. What day would yesterday be if Thursday was 4 days before the day after tomorrow? So I figured the easiest way that I could think about doing it was to set up, make that a little bigger. We have today, we have tomorrow, we have day after tomorrow, and we have yesterday. So what day would yesterday be if Thursday was 4 days before the day after tomorrow? So this is the day after tomorrow. So if I go back 1, 2, 3, 4 days, this is Thursday. So yesterday was Friday. Today is Saturday. Sunday would be tomorrow. And Monday would be the day after tomorrow. So it's asking for what day would yesterday be. So yesterday was Friday. Okay. Let's look at where we left off. We had a program. Let me bring that into today's. And edit, paste to machine. And let's get rid of a lot of the junk. Okay, so we were asked to, let's just go through this one quickly.
Oh, I'm sorry, Professor. I'm looking at like the thing that I had sent you before. Before you like go through that, can I actually just take a picture real quick and resend it to you again? Because apparently it didn't send right.
All right, do it right now.
Yeah, I'm doing it right now, right this second. Sorry about that.
Okay, so you were asked to calculate VBC using voltage division. Between B and C is R2, so that's the resistor we want to use in the top. So we can say that VBC is R2 over, I'm just going to put the sum of the resistances, we'll put in the values in a minute, times VS. So if I do that, I've got in the denominator 10K plus 6.8K plus 1.2K plus 12K plus 10K. And in the top, we put the resistor we want to find the voltage across. So remember the rule was, this is the resistor we want to find the voltage across. This is the sum of the resistor, and we're going to multiply that times V sub S, which in this case is 36 volts. So VBC, when all is said and done, the sum of the resistors turns out to be 40. VBC turns out to be 6.12 volts. Okay. The second one is calculate P sub R3. Well, if we think about our table, let me put the table up over here. We had VS, R1, R2, R3, R4, R5. We had the resistance. current, voltage, and power. Putting in what we know, oh, nuts.
Mm.
No, I can't.
Hey, Professor.
Yeah.
Sorry, I think I muted myself. For some reason, for the first answer, for like number one, I accidentally didn't use voltage division. I used the regular way first. And then I got the correct answer, which was 6.12. But then when I used voltage division, I ended up with the wrong answer. So I'm not quite sure
All
what
right.
I did wrong there.
What you're going to do on the calculator, remember, is you're going to put in, if you do everything in K, since every single unit, every single resistance is in Ks, the Ks on the top and the Ks on the bottom come out to be canceling each other out. So you could just put this in as 6.8 divided by left paren 10 plus 6.8 plus 1.2 plus 12 plus 10 right paren times 36.
Oh, okay, I see what
If
I
you
did.
don't put the parentheses in, remember PEMDAS, it's going to say 6.8 divided by 10. That's a division plus, well, division takes precedence over addition. So it's going to do this division first and then add and then add and then add and then add and then multiply. So it'll probably multiply this before you get done. So you got to remember order of preferences and that the parentheses are important in the denominator.
Okay, I gotcha. Thank you. I just checked it. Okay, I got it.
All right, so R1 is 10K, R2 is 6.8K, R3 is 1.2K, R4 is 12K, and R5 is 10K. And we just figured out that VBC, which is the voltage across R2, is 6.12 volts. So you were asked to find the power in resistor 3. Well, if I look at it, remember, we always need at least 2 items in a row to be able to solve for any of the other items. So I can't find the power here unless I either know the current or the voltage. So which one am I going to solve for? If I find the current, can I use that to find the power?
Yes.
Yeah. If I find the voltage, can I use that to find the power?
Yes.
Yes. So which one am I going to use?
Whichever.
Read number 3.
I'm sorry, what do you mean? Read number
Well,
3.
if I solve for the current, I can solve for the current, and that's the current everywhere, right? So that will
Yep.
give me the current for R3. So I could use that to find the R5 rather. I could use that to find the voltage across R5. I could also drop back and use R5 to find
Yeah.
R5 using voltage division. But let's solve for the current. So if I solve for the current, the first thing I need to do is calculate RT. So R, or REQ, is going to be R1 plus R2 plus R3 plus R4 plus R5. So I've got 10K plus 6.8K plus 1.2K plus 12K plus 10K. So the REQ is 40K. And now IT is VS over REQ. So I have 36 volts divided by 40K gives me 0.900 milliamps or 900 microamps. And then P sub R3 is I sub R3 squared times R3. So I've got the 900 microamps squared, oops, times 1.2K. And that should work out to be 972 milliwatts.
Yeah. Yes, sir. I didn't use a table like when I did the homework. Is that okay? I just did that.
Yeah, no, the table, you don't need to do the table. I just find that, especially for people who are doing this at the very beginning, they're just learning this, the table helps because what it does is it allows you to look at it and say, okay, I need to find in any row or column, I need to find at least two things to find the third. So that is an easy way to look at it and say, okay, this is the only place I've got, and only row I've got two things. So I've got to find something using this. So if you didn't use it, that's fine.
Okay. Thank you.
The third thing was find VE. Well, E to ground is 5 volts. R5. So I can say it's IT times R5, or I could write this as I sub R5 times R5, since the current through all the resistors in the series is same. So it's 900 microamps times 10K. Works out to be 9 volts.
Mm-hmm.
Okay. We talked a little bit about double subscript notation, and while we're in this problem, let's do one more calculation. We figured that one out. Let's calculate VAB, and that's going to be IT, well, let's call it I sub R1 times R1, which is the same as IT times R1. So we have the 900 microamps times R1, which is 10K. So that also works out to be 9 volts as a value. The reason I calculated that is, what happens if I ask you to find VAC, not A to B, A to C? Well, in a series circuit, if I'm looking at the voltage between 2 points that are not on opposite ends of a given resistor, like A to C, what we can do is we can say that the voltage A to C is the voltage A to B plus the voltage B to C. All right. So I could turn around and I could say VAC is going to be VAB plus VBC. All right. Now what we need to do is we need to figure out what's positive, what's negative. We figured out that VAB is 9 volts. We figured out that VBC is 6.12 volts. But we need to put in polarities. So if I think about VAB, is plus on the left end of the resistor or the right end of the resistor? The 9 volt, plus on the left, plus on the right.
It's on the left.
Plus on the left. Remember, how do we determine that?
Well, when you're looking at the source of the volts, like 36 volts, the positive side is on the top. So that's going to be where like the voltage is coming from. And so it's going to enter to the left and leave through the right.
Yeah, okay. We always look at the current. I'm glad you got to that. We're always going to look at the current. Current leaves the positive of the battery, goes through the circuit, and returns to the negative of the battery. So current goes into the left end of the resistor. That makes it the positive end of the voltage drop, and leaves the right end, makes that the negative end. Current goes into the left hand of the voltage, the resistor, and leaves the right end, makes that negative. We said that when we looked at a double subscript notation, like VAB, the first subscript, whatever the polarity is on that first subscript, that's the polarity we use. So VAB, plus is at the A, the first subscript, so that would be positive. VBC, the B is at the plus end, so that's the positive. So we would write this as plus 9 volts plus, what was it, 6.12 volts? So VAC works out to be 15.12 volts. So I could say up here that between here and here, I have 15.12 volts, plus on the left, minus on the right. So if I took a multimeter and put a multimeter in the circuit and measured AB, I'd read 9 volts. If I measured VBC, I'd measure 6.12 volts. If I took my multimeter and put my red lead at A and my black lead at C, I would measure 15.12 volts. Okay. Questions on that?
And then it's plus
because we calculated it to be a plus value. So we said that VAB was positive because when we looked at the 9 volts, the plus was at the A end, right? And we said the plus was at the B end, so that's why this was plus 6.1 volts. Because this is positive, when we calculate it, that positive gets tied to the A end. So that means that when I go up here, the positive is going to be tied to the A end, and the negative would be at the C end. That clear it up a little?
Yeah.
That was a definitely maybe.
Yeah, no, I get it. Thank you.
Okay. All right. Let's see. You already have one of those values. All right. Well, we got this up. Calculate. Let me bring this down. God bless.
Thank you.
Calculate VCD. Oops, I wrote the V already. and then calculate VBD. And then calculate VCA. So take a couple of minutes, try those. How we doing? How many people are, well, yeah, I was just like, you can raise your hand. Let's take a look at it. There's a bunch of different ways you could solve for VCD, but the easiest, since we already have the current, is to say that VCD is just I sub R3 times R3, which is IT times R3. Somebody's going to make the argument that if we use voltage division, the advantage to voltage division is that we're using all given values. But to make things shorter, VCD between C and D is R3. So it's just going to be I sub R3 times R3. But because this is a series circuit, I sub R3 is equal to IT times R3. So we have the 900 microamps times 1.2K. And that works out to be 1.08 volts. VBD in order for me to get from B to D, I have to add from B to D, I have to add up this voltage plus this voltage. So when I do that, it's VBC plus VCD. So the values are 6.12 and 1.08. And if I look at it, it's VBC. So we look at B and say, okay, that's the plus end. So that's going to be a positive for the 6.12. And if I put in the 1.08 volts, current comes around, goes into the top end of R3, makes that the plus end, leaves the minus, the bottom end, makes that the minus end. So for CD, C is linked to the positive. So we would have plus 6.12 plus 1.08. So VBD is going to be 7.20 volts. Any questions on that so far?
Not really.
Okay. Just let me reply back to somebody on a question.
How about VCA? Does you have to calculate like from CD, DE, and then EA, or we have to like just go backwards on C and A?
Well, we're going to do it both ways. So the question, the next part is find VCA. So I have two ways I can go. I can go from C to A this way, which would be R2 and R1, or I could go C to A from C to D, D to E, E to ground, ground to A. And we're going to do it both ways, and let's see what happens. So if I go with the top route, going this way, it's going to be, I'm going to add, to get from C to A, I have CB and then BA. So I'm going to add VCB and then VBA. So if I do that, VCA is going to be VCB plus VBA. Well, the values up here. CB is 6.12, BA is 9. So CB is 6.12 and BA is 9.0 volts.
We're using the negative numbers.
Well, yeah, we're going to get to that. So if I look at CB, first subscript in that is C, and we look at the voltage associated, here's the voltage over here, the negative is associated with the C. So VCB is going to be negative 6.12. Then we look at VBA. B is the first subscript. We look over here, we see the negative, so that it's going to be negative 9 volts as well. So if I do that, this is a negative 6.12 plus a negative 9 volts, gives me a VCA value of negative 15.12 volts. Remember back when I said, if you think about a voltmeter, the first subscript is where you put your red lead, and the second subscript is where you put your black lead. So if I put my red lead on C and my black lead on A, I get negative 15.12. So if I put my red lead on C and put my black lead on A, I get negative 15.12. If I put my red lead on A, where is it down here? Put my red lead on A and my black lead on C, I got positive 15.12. So which is right? V sub AC is equal to positive 15.12, or V sub CA is equal to negative 15.12. Now is when somebody replies. Which is right? VAC equals plus 15.12, or VCA is equal to negative 15.12.
VCA is equal to negative 15.12. And then you said AC?
AC is equal to positive 15.12.
Both are correct.
They're both correct. It's the same thing. Right? If I look in my circuit, it's the same thing. All right? We're both telling you the same thing. All right. So let me go back to Carl's question. Do we go this way or do we go this way? So if I go this way, I have to add CD plus DE plus E plus ground to A. Let me just, for the time being, for this one, just to avoid confusion in the subscript, let me just put a G subscript down there for ground. So I could also say, wow, just about enough room to do it, or VCA is going to be VCD plus VDE plus VE to ground plus V ground to A. So it would be C to D, D to E, E to ground, ground to A. 1, 2, 3, 4 terms. So what do we put in? For CD, the value is 1.08, and C is the first subscript, so it's a plus 1.08. So down here I've got 1.08. VDE, D to E, did we solve for that somewhere along the line? Guess we didn't. Let's solve that quick. VDE is IT times R4. So 900 microamps times 12K, 10.8 volts. All right. What was VAB? It was 9 volts? Yeah. So if we go up here, this is going to be, oops. Plus on the left or plus on the right?
On the right.
On the right. Current's going clockwise through the circuit, so it goes into the right-hand end first, makes that the plus, leaves the left-hand end, makes that the minus. And while we're at it, we might as well put in VE, which we figured out before to be 9 volts. And again, current goes in on the right, leaves on the left. So VDE is going to be, I could shrink this screen just a little bit. VDE is 10.8. And if you look, the D end is the positive end, so that stays positive. VEG is 9 volts. And the E end is the plus end, so it stays positive. And then we have VGA. Well, if I go from G to A, which end of the voltage do I hit first, the positive or the negative?
Negative.
Remember, the long line is the positive, the short line is the negative. So if I go from G to A, I hit the negative side first. So that means that this is going to be plus a negative 36 volts. That means VCA is going to be, how much? If you add these and then subtract it from 36?
0.
Nope.
No.
Because you don't have all the, it only adds up to zeros if you add all the voltages. We did not adding all the voltages around the loop. We left 2 resistors out.
Oh, it would be the same thing as the negative, like 15.
So this is what, 11.88
Mm-hmm.
plus 9 is 20.88.
Mm-hmm. And then minus
20.88 subtracted from 36 is negative 15.12 volts, or negative 36 plus the positives. So Carl, to answer your question, long way around, whether I go the short way,
Or the long way is the same thing.
yep, exactly. So if I go from here to here, I get the same result as if I go around all of this. So 9 times out of 10, you're going to take the short path. There may be something that prevents you from going this way, maybe an unknown value or whatever. So that would allow you at least to now go this way to figure out the unknown value. Okay.
Thank you.
Any questions on series circuits before we leave it and start into parallel? Let me just do one thing on series as a lead into parallel. We said before, it's on a new sheet. Oh, I know what it is. So here's my circuit. if I did a list of R1, whoops. R1 connects between point A to B. R2 connects between B and C. R3 connects between C and D. R4 connects between D and E. R5 connects between E and ground. If I look at any two resistors, do any of them share the exact same letters? R1 has A and B. R2 has B and C. So R1 and R2 share a B, but the other ends don't match. 2 and 3 share a C, but the other ends don't match. 3 and 4 share a D, but the other ends don't match. 4 and 5 share an E, but the other ends don't match. And if I went back to from 5 to 1, they share nothing in common.
Would you, if you were going from 5 to 1, would you never say from ground to A?
Well, if you're looking at connections, in other words, I'm just looking at the resistor connections. Because remember, even if I drew this way, even if I drew the circuit that way, those resistors are still in series.
Mm-hmm.
This would be A, this would be B, C, D, E, and ground. They look physically like they're drawn parallel to each other.
Mm-hmm.
But if I went and said, all right, R1 connects between what two terminals, R2 connects between what two terminals, you'd end up with this table.
Mm-hmm.
All right. And that's going to be important to remember. I'm bringing this up now because in a minute, we're going to look and see what a parallel circuit looks like.
Mm-hmm.
So let's talk about a parallel circuit. Just as a point of information, most of you probably already know this, but for some people, it is always interesting to see what I get. There's one R and two L's, three L's actually, two L's and then the last L. For some reason, I get people who spell it P-A-R-R-A-L-E-L, P-A-R-R-A-L-E-L-L. It's really interesting, but it's one R, two L's, and then a last L. So let's look at a parallel circuit. I've just drawn it with 5 circuits, and 5 resistors. Could be 2, could be 3, could be 4, could be 5, could be 25, whatever. Give you a minute to jot down the circuit and then. While you're jotting down the circuit, have you started using multisim in lab yet?
Yeah, we did. Personally speaking, like I downloaded it and it wouldn't really open up for me. So we were supposed to use it today, and we also used something called Virtual Breadbox, which was pretty cool. Not Breadbox,
Virtual breadboard?
Breadboard.
Oh, okay. Because there is a breadboard in multisim too. I have to remember that virtual breadboard and look at that. I think Professor Atwood mentioned that to me and I forgot about it.
It was cool, but there might have been like an error or something because we tried to do something with like LEDs, and according to the connection, like the LED should have turned on, but for whatever reason it refused to.
Okay. I'll have to look at it. Okay, so let's look at this for a minute. If I look at this, this is a wire that goes to here and a wire that goes to the resistor, and that wire continues to here to this resistor, continues here to this resistor, continues here to this resistor, continues here to this resistor. One of the things, and we don't do it really in series as much, is we can talk about a node. And if I look at a node, the node is the wire, and the wire goes along here. This is all still part of the wire. 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 So all of this is one node.
What can a node be defined as in this case?
A connection of components. A common connection for components. So if I was going to label this node, I could just call this node A, give it a name. If I wanted to, I could go back to the series circuit. I'm going to go back to where we were in a minute. So this is node A. This is node B. This is node C. And the way I'm drawing the node is, I started a resistor, go alongside the wire until I get to the next component. I don't go through the component, I jump over and double back along the side of the wire till I get to the component, and then I jump over. So if I started here, I go along the side of the wire, I get to the next resistor, jump over and double back. So that's another node. I go along the side of the wire. If I get to another wire, I turn. This is like a component, so I jump back. I go alongside the wire. When I get to the next component, the battery, I jump over and double back. Alongside the wire, I turn. So the only time I cross a wire, I go alongside the wire, and the only time I cross over the wire is at a component. So I crossed over here at this resistor, I crossed over here at the battery, I crossed over here at ground. When I was looking here, I went alongside the wire till I got to the resistor, crossed over, and then doubled back to my same resistor. So everything along here is node A, everything along here is B, everything along here is C, everything along here is D, along here is E, along here is G for ground. All right. So when I did it over here, I started, I went alongside the wire. I got to where the wire was over here, but I don't want to cross because that's not a component. So I went down along till I got to the component, crossed over, doubled back. I don't want to cross the wire here. I'm going to turn and go alongside the wire. Got to the wire here. I'm not going to cross over. I'm going to go turn and go down alongside. Got to a component, so I jumped over, doubled back. Don't want to cross over here, so I turn and go alongside and kept on going there until I got all the way to here and came back to my original starting point. Does everybody see how I got that?
Yeah.
So now, if I start here and go along, I go alongside the wire, I turn to follow the wire, along here. Now I'm at a component. So I was going up, I'm going to jump over and then double back to go down. I go along here. I don't want to go over the wire, so I'm going to turn and follow the wire. Now I'm at a component, so I jump over and double back. I go down. I don't want to jump over this wire, so I turn and follow alongside. Go up. I'm at a component. I jump over and double back. Alongside, I turn. Jump over and double back. Alongside. Get to here, I turn. Jump over. Double back. Alongside. Turn alongside. Now I'm at a component. I jump over. I'm back where I started from. So all of this is the same, electrically the same place. We'll call that B. So this would be node B. Everybody follow how I labeled the nodes? Any questions on that?
Just one.
Mm-hmm.
So I'm seeing that when you're doing that, you're not going through the component. Is that why it's voltage across? Because it's going across like the whole entire thing, but then it's current through because voltage can't go through the component, but current can?
Sort of, but what really I'm just trying to do here is define what's a node, what connections form a node. So in other words, this connection, where's my, here I am. This connection for the battery, this connection for the resistor, this connection for R2, this lead for R3, this lead for R4, this lead for R5 are all connected to node A. So this interconnection of all of these parts forms node A.
Okay.
And then this interconnection of the bottom of the battery, the bottom of R1 on bottom of R2, bottom of R3, bottom of R4, bottom of R5, that all forms node B.
Okay.
So now, if I do that same thing, and I make a list of the connections, what two nodes does R1 connect between?
I guess A and B.
What does R2 connect between?
Isn't that the same for all of them?
Isn't that the same for all of them? So in a parallel circuit, we say that the components share the same two nodes. So in this particular case, the two nodes they share are node A and node B, because they all connect to node A on the top, they all connect to node B on the bottom. Doesn't matter how I draw the circuit, they all connect to the same two nodes. One of the things especially when we get to series parallel circuit, one of the things I usually have my classes do is do a list like this. And if I see two components that are sharing the same two nodes, I know those two components are connected in parallel. If I see two resistors that share one lead together, in this case, they're all the same. But if I see one where one lead is the same and the other two are different, I know those are in series. So we'll use that as a double check on us to figure out our series and our parallel connections when we get to series parallel circuits. If I introduce it now, it'll be secondhand to you by the time we get to do it. So a parallel component shares the same node. Wait a minute. So what does VS connect between?
Um,
What two
Same.
nodes? Say, what did you say, Melvin?
AB, same nodes.
A and B, the same nodes. So wait a minute. So then V sub R1 would be the same as V sub AB, right? Because it's connected between A and B. And V sub R2 would be V sub AB. And V sub R3 would be V sub AB. And V sub R4 would also be V sub AB. And V sub R5 would be equal to VAB. Yes? If I took
Yeah.
a meter and connected it across R1, I'm connecting from A to B. Across R2, I'm connecting from A to B. R3, I'm connecting A to B.
Why is there no ground?
Oh, all right, we can put ground in over here.
Oh, okay.
So then what do you think you can tell me about the voltages in a parallel circuit? Each of the resistors, the resistor voltages in a parallel circuit.
It might be less in each resistor because it goes to it, kind of, or
Wait a minute, hold on.
Can
We
you repeat
just
the
figured
question?
out that VR1 is VAB and VR2 is VAB and VR3 is VAB and VR4 is VAB. So what can you say about all of the voltages?
They have the same voltage.
They're all the same. All parallel resistors have the same voltage. Got to put in all the words helps. So resistors in parallel have the same voltage. This is really all resistors in parallel have the same voltage. Not all parallel resistors. So if you have a different circuit, obviously you're going to may have a different voltage. And in this particular case, if we look over here, in this particular case, in a simple parallel circuit, the resistor voltage equals V sub S. Key words. In a simple parallel circuit. So if we have resistors that are in parallel in a complicated circuit, does not mean that it equals V sub S. They'll have the same voltage, but they won't have equal to V sub S. Only in a simple parallel circuit, which means we've got some number of resistors in parallel connected across the source. This is my simple parallel circuit. So rules for parallel circuit. The first rule is resistors share the same two nodes. The second one is all of the resistors have the same voltage. If I had, well, give me a minute to finish writing.
Mm. Hey, can I ask a question, Professor?
Sure.
So then, if the resistors have the same voltage, does that mean that the resistors have the same value? And if they
No.
don't, then does that mean that their currents are going to be different?
I did not pay you to ask that question, correct?
No.
Because that's exactly what I was going to bring up next. I love it when it works out. Okay, so the question is, if the voltage over here and over here and over here and over here and over here are all the same values, let's say this was a 1K resistor and this was a 2K resistor. Using Ohm's law, and remember Ohm's law always works, if I took whatever that voltage is and divided it by 1K and took that same voltage and divided it by 2K, what could you tell me about the current in the second resistor compared to the first? Bigger, smaller, or the same?
Smaller?
It's going to be smaller because of the fact that you've now divided it by 2K instead of 1K.
Mhm.
So the currents in each resistor will be different unless what?
I guess resistors have same value.
Unless the resistors are the same value. So let's see. I'll give you a minute to finish writing and then I'll. Anybody need more time?
No.
Let me just see something because somebody just brought something up. I think I might have had a calculation on the other error. I'm going to double check something later. There might be a calculation error on that other problem. All right. If we think about series circuits versus parallel circuits, in a series circuit, we said two resistors in series only share one common node. In a parallel circuit, resistors in parallel share two common nodes, or share two nodes. In series circuits, the current is the same in each resistor. So in a series circuit, the current is the same. In a parallel circuit, the current in each resistor is different unless all resistors are equal.
Professor, why would there be a parallel circuit wherein like all resistors basically are equal? Like, what would be the point then? Why wouldn't they just have one?
Sometimes you can't get the value you need, so you put a couple of resistors in parallel to get a specific value. Sometimes, and this is probably the most common case, sometimes you're trying to make up something called a dummy load, which is like a resistive load. So sometimes, let's say I have an amplifier. Rather than hook up a speaker to it and keep my neighbors up all night, I can hook up a resistor to it and test the circuits in the amplifier, and the sound power will go into the resistors where it's dissipated as heat, as opposed to coming to a speaker and making all kinds of noise. And we can talk more about that, but I just looked at the clock quick. Bring that up at the next class, and I'll talk about it a little bit more, because I want to get this last point in. In a series circuit, the voltages across each resistor is different unless resistors are equal. In a series circuit, the voltage across each resistor is the same. So the key ideas here that you want to get across is that in a series circuit, the current is the same. In a parallel circuit, the voltage is the same. All right. So in series, we have the same current. In parallel, we have the same voltage. Okay. Questions?
Is there such a thing then where there's a circuit where the resistor would always be the same between the components?
In which? Series
No,
or
not
parallel?
in this one. Neither. Like I see series, its current is the same, parallel voltage is the same. Is there such a thing where like the
Oh,
resistors?
the resistance in it? No, because all we've really got is the series circuit and the parallel circuit.
Okay.
Professor Atwood just joined us. Did you have something you need?
Okay, I found this on the web for circuit
Oh,
and a parallel circuit.
Go away. The
Um,
did you have an announcement to make or something?
yes, so we were going to have a virtual lab today, okay?
Okay.
And is Asan there, perhaps?
Yes, he is. He's going to talk to
Okay,
me after
good. So
class.
Asan, you're going to join us for that lab because you have to just call somebody at the college when you get a chance.
Oh, okay.
All right. So I sent you guys the link in your email for that for the virtual lab, right?
Yeah. Hey, Professor. I'm sorry. I don't
Yeah.
know if it's like too much
Which
to
one?
ask. Oh, huh. So
Oh,
I
yeah.
don't know if it's like too much to ask. I know that our class basically like starts at like 2:30 and such, but we're gonna be there. Basically, we started at 1, and we're gonna be with you until like after 5. Could we maybe
Right.
have like a little break or something before?
Sure. Absolutely. Definitely, that's a good idea, right? Recharge your batteries a little bit, and
Trying to get some food.
get some food. Absolutely, you need some energy, right? So then we'll definitely start at 3 o'clock. If you want to stop by a little bit earlier and hang out with me, that would be fine too. But we'll definitely start at 3 o'clock for the lab session.
Professor Atwood, your food bill must have dropped dramatically with these virtual labs.
That's true. I got
Professor Atwood was known for bringing food into labs, especially the 8:30 classes. He was working with oranges, and so I figured with virtual labs, his food bill must have gone down dramatically.
Wow, you just really got played all throughout COVID.
Yeah, he lost on 11. All right, before I forget, any last questions on series versus parallel? We're going to do more with series on parallel on Tuesday, and we'll do some calculations. And I also was going to bring up, but we ran out of time, a multi-sim of that one circuit with the two 10K resistors, the 12K, and the other two resistors that we sort of beat to death, and take some measurements in multi-sim. What are you doing today in lab?
So I guess we'll do a multi-sim simulation of a series circuit.
All right, so they already did the calculations. We did a whole bunch of calculations. I should send you a screen capture of what we did. You could use that circuit. They could take measurements and see whether or not we screwed up our calculations or not.
Oh, that's a good idea. Excellent. They have the circuit themselves, right? So they should be able to provide me with the specifics.
They should. Yep.
You don't quite trust them.
I didn't say that.
Okay.
That's hurtful, Professor. That's hurtful.
No, well, after
The
doing this for 40 something, almost 50 years, you sometimes get a little cynical, having seen
Yes.
a lot of things.
So Natasha will give us the specifics.
Yes.
Excellent.
Okay.
Good. Very good.
Okay.
And then what we'll do is we'll put it into an Excel spreadsheet and we'll get Excel to calculate out the results also.
Oh, there we go.
Good.
What do you got today? 103?
No, 112 this class.
Oh, 112 lab.
Yep.
Yeah, right. Okay.
But that's like what they were saying, right? They're in class since 1 o'clock doing this stuff.
Right.
It's
Yep.
brutal.
I hear you. And they don't even get up to walk across the hall or anything.
Right.
They get to walk across their bedroom, and that's about it. All right. Are there any questions before I close the meeting and let you take a quick break?
About
Wait a minute. Hold on a second. Wait a minute. Professor, you're starting at 3?
3, yes.
So that means I can really go to like 2:45, right?
No.
Be my guest.
Okay. Are there any questions before I close the meeting? Hassan, we're gonna talk to you. Yeah. Wait till everybody leaves, and we'll figure out quick what's going on. Why don't you stick around?
Hassan?
No, you.
Yes, I'll stick around. And Hassan, you have to call somebody on campus.
All right. So let me close. Everybody can leave except for Hassan and Professor Atwood because we have something we got to cover. Otherwise, everybody else have a good weekend. See you on Tuesday.
Okay. Bye. Feel better,
Bye.
Hassan.
Yes, Hassan, how are you feeling?
Oh, I'm good now. Like, I'm good.
Let me just bring up my screen of where, oh, here it is. I just want to see who's left so that we have a discussion sort of in private.
Right.
Okay, so I'm going to, if you're still in the meeting, I'm going to eject you from the meeting if you're not one of those two people. So I'm going to remove a couple of people who might not be here. So we're
Good.
going to